Not in supernovae.
All right. Thank you very much. Normally I say thank you for inviting me, but I did invite myself as one of the organizers, so that's not quite right. But anyway, thank you all for coming. Yes, I was going to talk about, oops, I'm going the other way. Hold on. Come on, stupid thing. This way, yeah. Okay, so I am going to talk about the shoes measurements of the Hubble constant, but I liked this cartoon. So you can find this in Symmetry Magazine. As I said, I had to guess which was late and early. I guessed this was late because these people are actually measuring H0, whereas these people seem to be doing a lot of calculations. No offense meant to anybody. But anyway, okay. So a century of cosmological research has led us to the standard model, as we have it today, of cosmology, vanilla lambda CDM, with its 6 free parameters, a number of ansatz, dominated by dark sector components with unknown physics. We make some simplistic assumptions about the dark parts in particular, and when the standard model looks like this, that is before recombination, we use that model to predict the physical size of fluctuations, including the sound horizon and including the baryon density. We then measure the angular fluctuations in the CMB, or alternatively, we measure the baryon density. And by comparing those, we have essentially calibrated this version of the model. Then, over 13-some billion years, the model evolves to look more like this, during which we predict from the model the expansion history of the universe. Now, tools like baryon acoustic oscillations and high redshift supernovae, they're sort of the guardrails for the model, I would say. They don't tell you you're on the right road, but they keep you from going off curves on the road that you're actually on. And then finally, the model predicts the value of the Hubble constant, 67.4 plus or minus 0.5. So this is a better than 1% prediction. And so a test of this whole story, including the uncertain bits, is to try to measure the Hubble constant to comparable precision. And I think our job is to put aside any sort of Bayesian priors that the model is right or the model is wrong and just go ahead with the measurements. And so we started a project called the Shoes Project a number of years ago to try to reach percent level precision in measuring the Hubble constant. And many of my colleagues from that project are here, and they will give better talks than I will on various parts of this. So I'm going to sort of set the table more, as well as for some other talks. But we built a strong and simple distance ladder, just geometry done a number of different ways to calibrate Cepheids and to calibrate type 1a supernovae. Cepheids, of course, are pulsating stars whose period correlates strongly with their luminosity, and type 1a supernovae, of course, are exploding stars near the Chandrasekhar limit. Now, I'm going to move over here to this side. One of the ways that we expect to reduce systematics along the measurement is by collecting consistent data along the ladder. And I'm going to talk about what I mean by that at various junctures, as well as by making observations in the near infrared. In addition, we think that we can carefully keep track of the systematic and statistical errors using the covariance of the model parameters and the data along the way to get a realistic error bar at the end. And so, just jumping to the point, here's where we are after 15 years of doing this. We have 5 geometric sources that are used to calibrate Cepheids. There are 19 galaxies where we have observed Cepheids and type 1a supernovae, and then hundreds of supernovae out in the Hubble flow. And as I said, the rest of this talk, I'm going to walk you along this and point you to other people's talks. We're right now at 74 plus or minus 1.4. And yes, this is in 4.4 sigma tension with lambda CDM. Now, I want to direct you to 2 goals to think of throughout this talk. The first is what I would call the tension level, 0.2 of a magnitude. That's big. That would be, I think, hard to get wrong if we're careful. A much tighter goal, 10 times tighter, is what we would be trying to measure to, which is 1% or 0.02 magnitudes. That is really hard. Even if we try really hard and are very careful, this will still be a challenge, and I will address that later on in the talk. So let me start out with the first step, the geometric step. In the geometric step, you essentially measure geometric distances to calibrate Cepheids. Now, there's actually two parts to this. There's having good geometric distances, that's of course very important, but also having consistent Cepheid measurements. And what I mean is that you measure those Cepheids the same way you're going to measure the next set of Cepheids further up the ladder, otherwise you introduce systematic error. If you do a great job here, but there are inconsistencies there, then you may have lost some of the precision that you had. And so we're going to hear at this conference about at least 5 sources of geometric distances that are all good to about 3% or better. 3 of those are 3 flavors of measuring Milky Way parallaxes. 2 by the Hubble Space Telescope, fine guidance sensor and scanning, and we're going to hear a lot about Gaia as another way. We're going to hear a great talk, I'm sure, from Gregor Petrinsky about this beautiful work on detached eclipsing binaries in the LMC, and we're going to hear from Mark Reed about improvements in measuring the masers in NGC 4258, so and related talks in these as well. Now, let me say something about measuring consistent photometry of Cepheids along the distance ladder. We've put a lot of thought into this because it's not trivial. You're looking at sources which are, in astronomers' terms, 24th to 25th magnitude, and then the various anchors are much closer, so the Cepheids are much brighter. And if you want to get all the way to the Milky Way, you're talking about a factor of 1,000,000 in flux, and guaranteeing that you haven't introduced some systematic error along the way. And so the importance here is to get linear measurements, to do them on the same photometric system, over the same range of periods, and the same range of metallicity. And that's something that we've been putting a lot of attention into recently. So I'm going to jump off and just show you a little bit about measuring Milky Way parallaxes with spatial scanning, largely because I sunk about 4 years of my life into trying to do this, and it's very hard. I really respect the Gaia people, but it is doable. Stefano Casertano, who was here, and I developed a method to spatially scan the Hubble Space Telescope to measure parallaxes with 20 to 40 micro-arcsecond precision, and then we did that for 8 Milky Way Cepheids over the course of 4 years. So we watch these things go back and forth. We measure the amplitude, that measures the geometric distance, and it also does it on the HST system. Now, spatial scanning can give you very high precision astrometry. It can also give you very high precision photometry. And so in anticipation of Gaia measuring many more and better parallaxes, we also picked a set of most of the known 50 Milky Way Cepheids with long periods, and we measured their photometry on the WIF-C3 system using the spatial scanning so that we can marry these together with the Gaia parallaxes. And I think we're going to talk about Gaia parallaxes. Based on DR2 and self-calibration, this gave an independent 3% calibration of the Cepheids. We have a program in cycle 27 that we think will help improve the calibration of Gaia as it relates to Cepheids. But as I said, we'll talk more about that. I think Stefano will talk about that as well. So here's where we stand today with the period luminosity relationship of Cepheids in the Milky Way calibrated by parallaxes. These are the 3 different flavors we have. These 2, the spatial scanning data shown here in this kind of bluish color and the Gaia data in red, both have the virtues that they have been measured photometrically on the same system as the extragalactic Cepheids we'll talk about, and over the same period range. Now, if Anthony gives us a talk and tells us we can expect Gaia to reach the final precision that they hope to get to, that would be very exciting because it will turn these 50 calibrators into a 0.4% calibration of the Hubble constant, which would be great, provided we can get there. So I think that's something we will be talking about in this conference. Now, with Gregor Petrinsky's detached eclipsing binary distance to the LMC, we used the Hubble Space Telescope to directly observe the Cepheids in the LMC so that we can do a 0-point independent measurement to the distant galaxies. And this also illustrates how nice the infrared is intrinsically, because as you go from the optical to the near-infrared, your differential dust is less and less of an effect. So we make our observations in the de-reddened H-band, or F160W, and that realizes a good improvement. I said something about flux calibration. Can we really compare fluxes over a factor of 1,000,000? Well, I would say as of this year, yes, we can without limiting our ability to measure the Hubble constant to 1%. This is a flux calibration ladder I built with Gautam Narayan and Annalisa Calamita, where we compare various kinds of sources, the true wide-field camera 3 magnitudes versus from other sources, from overlapping CCDs, and we've calibrated out a 0.3% count rate nonlinearity. The uncertainty in that will propagate to a 0.3% uncertainty in the Hubble constant. So I would say as of the last year, the Hubble Space Telescope has now been calibrated to allow us to make this very challenging measurement over a factor of 1 million in flux. Okay, so the summary after using these 5 different, and I would say pretty unrelated in terms of their systematics, geometric calibration, the masers, we're going to hear about an improvement from Mark Reed that gets this to 1.5%. The various Milky Way and the new detached eclipsing binary, these are all relatively consistent. They kind of bop around between around 72 to 75 or so, so consistent within about 1.4 sigma and pretty independent systematic. So the anchor step, this step, which used to be the hardest step in the distance ladder, I think is very robust at this point, and that is a nice piece of progress. Okay, on to step 2. Observing Cepheids in the hosts of type 1a supernovae. This is the rate-limiting step for measuring the Hubble constant locally, because you just can't see Cepheids out very far, and that's a small volume for type 1a supernovae. And so if you actually look at the number of type 1a supernovae, the good ones, the ones that pass the quality checks, as a function of distance, getting out to the 50 megaparsecs or so that we can with WIF-C3 limits us. We've done 19. This year, we're going to double that to 38. I would like to get to 50 to push the uncertainty, the rate-limiting uncertainty, well below 1%. But this will require nature producing more, but more importantly, the Hubble Space Telescope lasting for another 5 or 6 years. No guarantee for that. Just to contrast, I just want to point out, TRGB is a very good method. It doesn't go out as far simply because it's not as bright, so you can't do as many, but with future telescopes, JWST, I think we'll hear things about that potentially in the future. Okay, here are the 19 period luminosity relationships measured in 3 bands from Shoes, and Lucas Macri will be talking about that, so I won't say much other than we can measure these anchors similarly on the same photometric system. And as I said, we're in the process of doubling the sample to 38. These are some of the hosts that we're currently observing, and just a quick flash of some very preliminary period luminosity relationships from these. This is very rough, just did this last week, but it's clear that we have lots of Cepheids in these galaxies, so I'm optimistic that we will get those measurements. I'd like to say a couple words about how Cepheids are actually measured in galaxies. We did not invent these methods. These methods have been around for a long time. Peter Stetson is really one of the pioneers of multi-source photometry. We use his tools. And so we identify where the Cepheid is from the optical. We locate it in the near-infrared. We build a multi-source PSF, and we make those measurements. The residuals are pretty clean. What's nice is we can do the exact same process in NGC 4258, so that there's no difference there. And even the LMC now is quite similar, though less crowded than over here. Then, next step, we throw down fake stars in the vicinity of the Cepheids. We know their brightnesses. We measure those, and that allows us to remove the background or any effects of crowding. It also allows us to estimate the uncertainties in the magnitudes. These are the distributions of the fake stars. They're very Gaussian in log flux space. Last statement is just that the real scatter of the PL actually matches the error, so that's good. We don't have excess variance in this process. All right, step 3. We have a wealth of talks here on type 1a supernovae. Dan Skolnick, Dave Jones, Steve Rodney, Dylan Brout will all tell you in much better detail than I have time for. But just simply said, type 1a supernovae are the best tools we have for measuring the Hubble flow. We measure the Hubble flow over this intermediate range. We don't want to be too close, so we're not sensitive to local flows. We don't want to be too far out because we become sensitive to the other cosmological parameters. And so if we want to make this pretty limited to H0, this is the region. It's still gives us plenty of statistical leverage. Okay. Now, we have varied our analysis in many different ways to determine what the systematics would be, the ones that people have thought of or imagined. We've changed how we do outlier rejections. We've changed the reddening law that we assume for Cepheids, for supernovae. although we don't have much reddening for the Cepheids because we are in the near-infrared, whether we include a metallicity dependence or not, whether the PL relation is a single slope or two slopes, and the answers move around, but they don't move around very much because the samples are very well balanced. There's not a lot of lever arm for any one of these things, and so there's been many papers trying different things, and nobody has found a way to shove this around. There's been some attention on could the environments of the type 1a supernovae in the Cepheid host be different than the distant ones, and the easiest way to answer this is just to select the distant ones to be Cepheid hosts, that is, late-type galaxies, star forming. That encompasses about 2/3 of the distant ones. So when we do that, things don't change very much, but you're going to see, a good talk by Dave Jones, I'm sure, on this, because he wrote a very good paper on this just about a year ago. Okay, so what's going on with the measurements over the last 15 years, and this is going all the way back to Wendy Berry and other people on the KEY project. Lucas is here as well, using WIFPIC2 and the ground around 72 to 74, and the answer has remained in that range over the last 15 years, despite changing cameras, instruments, right? Then we used NICMOS and ACS, then we used Wide Field Camera 3, and of course, total recycling of the data. Now, there are new low redshift supernova samples coming online. Those will shift things around a little. I've seen the CSP and Foundation data sets. I think that will pull the Hubble constant down a little bit, maybe into the mid-73s by this route. Gaia, DR3, and then the doubling of the sample, we ought to be able to get to about 1.3% uncertainty. And then it gets really hard. I don't really know what to do after that. I'll address that at the end. Okay, so where are we? We're in this, I don't know, whether you're, depending on whether the glass is half full or half empty, we are in this interesting position right now where we see this 4.4 sigma tension between our latest choose measurement and the Planck vanilla CDM. And then looking at, there's been many reanalyses of our data set. It is now, you can get graduate credits at the University of Toronto in Joe Bovey's class by taking as a problem set, you analyze our data set and measure the Hubble constant. So what has taken us years, because we're not that smart, they can do now in 2 hours. So good for them. But people have thrown different data in here, near-infrared light curves for supernovae instead of optical light curves. Lloyd Knox is here, measuring the reddening law in each individual galaxy to see if that perturbs things, all kinds of different things. I really want to draw attention to the holy cow measurements. We'll hear more talks about them, but the reason I draw attention to it is it's the only thing that has nothing to do with anything we've done. I mean, it's also in the late universe, but it has no overlap. So I think that is interesting. In the early universe side, of course, there's a few different cross checks as well. You have different CMB data sets crossed with BAO. You have measurements of Big Bang nucleosynthesis. I think we're going to hear more from Graham Madison about this, but this looks pretty consistent here as well. Of course, if the late and early universe don't agree, we have to be open to the possibility of new physics. Again, we're going to hear much better talks. These are cartoonish ideas compared to, I think, what we will hear from real theorists, and so I don't want to waste a lot of time describing these when the people in the room who develop these ideas are actually here. Okay, frequently asked questions. I am frequently asked over and over and over and over, and I see papers again and again that we live in a giant void, okay, and that this is the answer. And so I will patiently explain this. So we would have to have about a 9% void. And there's two main reasons we know that this is not the case. One comes strictly from theory. There's been a number of very sophisticated n-body simulations done with large-scale structure, varying the position of the observer and the position of, and global. And you expect variations in the measured to observed Hubble constant of about 0.4%. And then a student of mine, Darcy Kenworthy, Dan Skolnick, and I, use the actual Hubble diagram itself. You can actually look for the inflection that would happen if we lived in a void. And so we did that. And there are variations, but those variations, starting from where we are at the 0.6% level. When people say we live in a large void, some people have said a specific large void, we can rule that out very strongly. To think about this as a void that would cause Planck is like 10 sigma. So, I mean, this in a very respectful way, please stop writing papers saying we live in a giant void. The data doesn't support it. The theory doesn't support it. It's a great idea. It just doesn't seem to be what's going on. Forgetting about the cosmological principle, the specialness of the location we have to live in. Sure, at the 0.5% level, but not at the 9% level. Okay. So, another question that's frequently asked, what if you use something else besides Cepheids, tip of the red giant branch, or miras? We're going to have great talks about that as well, but I want to give our perspective on this. Tip of the red giant branch, of course, is the brightest luminosity that red giants attain before the helium flash. There have been 10 high-quality supernova tip of the red giant branch measurements in the literature from the CCHP group and from Zhang and Li 2017. If we just take those 10 and swap them for the 10 supernovae, so the pink points you see here, what we're doing is we're swapping in those 10, but then you also have to state what is the calibration of the tip of the red giant branch. And with the great new Large Magellanic Cloud distance, you know, that is obviously a thing to do. But it's a little trickier. In order to define a calibration of tip of the red giant branch in the Large Magellanic Cloud, you have to state what the peak magnitude is of tip of the red giant branch, hopefully on the HST system, and how much extinction there is of tip of the red giant branch. I think we're going to talk about this more over this conference. If I just naively take what Zhang and Li had in 2017, which I think is using some pretty standard tools, then doing that, you get 73.2 plus or minus 2.2 for these 10 and the Zhang and Li calibration. Also, I want to give a shout out to Wenlong Wan, who's a student here working with me. He has a poster on how to do the transformation from the LMC to HST, because HST has not observed the LMC, which is unfortunate. Those same 10 give 73.5. So apples to apples, they seem to agree pretty well. But I direct you to talks by Wendy Friedman and Insung Zhang. We have done one so far, MIRA, in a supernova host. It looks like it's in good agreement, but the uncertainties are large enough that you can't really make a strong statement about that. Now, about TRGB more. We have been doing a kind of deep dive over the last few weeks on TRGB because we have one TRGB object in our sample, NGC 5643. So, you know, there's no way you learn more about a method than actually trying to do it. And so what we've been struggling with or realizing is TRGB is a really elegant method when you apply it in other galaxies, because you can observe it in the halos of galaxies and there's low extinction. But you have to calibrate it somewhere. And I think the calibration, and in particular figuring out how much extinction there is in the LMC, is the trickiest part, maybe even the Achilles heel. The TRGB I-band extinction is going to be then linear with the Hubble constant and the Cepheid calibration, and it's substantial. So let me first tell you the standard approach. What people have done is to use the Ogle reddening maps, which are made from red giant stars, red clump stars, at the exact positions of TRGB, and derive the extinction of those stars from those maps. And so this is a distribution of TRGB stars in the LMC picked optically or in the near infrared, and you get about 0.11, 0.10 magnitudes, okay? This is the same thing that Zhang and Li did, so I give that there, and this is what I did in the previous slide where I showed that you get a Hubble constant of 73. Other groups have done slightly different things. Earlier papers by CCHP have estimated the extinction by comparing the near-infrared colors of TRGB stars within the LMC, and recently published 0.05 plus or minus 0.05. It's a little bit higher than this, but it's within 1 sigma of this. Now, another method that people have looked at, we have looked at it, I think Wendy mentioned at Cosmo Gold that they were using as well, is to look at the TRGB colors themselves and compare those to TRGB colors in other galaxies, presumably galaxies with low extinction, to try to infer the amount of extinction. The tricky thing is, everybody loves TRGB in the I-band, rightfully so, because it's very flat in the I-band. That is, it doesn't have a lot of sensitivity to different ages and different metallicies. But that is not true in other bands. It's kind of hook-shaped, the tip of the red giant branch. So even if you come up with a linear color term and kind of try to rectify this, you still get large residuals because the dependence on age and metallicity are not the same. And so here are residuals that I'm showing. So whereas things are glorious in the I-band, in V you have about 1/10 of a magnitude going from like the LMC to like the SMC, about 2/10 of a magnitude in K and H. Here's where some of this data came from. So if you try to do the sort of standard thing that people do, which is a two-parameter fit. What is the relative distance between two galaxies with TRGB? What is the relative extinction? Then if you only had to deal with the measurement errors, then you could constrain both of those pretty well. In this case, I put in 1/10 of a magnitude, and I'm going to get back 1/10 of a magnitude. If you have to deal with these intrinsic metallicity errors, then the errors become quite a bit larger and really affect this process, and in particular can bias it, because if you're going from something like the LMC, which has higher metallicity, then to the SMC, the bias can be pretty significant. Here's a two-parameter fit of this. I can get back the 1/10 of a magnitude I put in without the bias from metallicity, but with the bias from metallicity, this is going to shift this by, in this simulation, I did about 1/10 of a magnitude, or 5% in the Hubble constant. So I think this is something to watch out for. Could we use models to correct this? Maybe we could. I think, we've discussed this some with TRGB teams, and I think we'll keep discussing this as well. And, my 2 cents is that the OGLE maps appear more robust because they're done as a function of metallicity, and so they're not sensitive to metallicity, and they've been vetted by other teams. Okay, now let me move on to the final part here, which is questions that keep me up at night. This is a big question. How old is the universe? We like to say all the time, it's 13.8 plus or minus 0.02, and I understand where that comes from. But that same route also predicts a Hubble constant, which right now appears different than what we observe. So can we really keep saying we know the age of the universe this well when we're about 9% off in the related 1 over h0 quantity? I'm hoping Lee Taverde is going to talk about how well we know ages. But I'm concerned, and I don't want to bum out the CMB people, but maybe we can't keep saying that we know this. Or at least I think we have to give a little more thought to what we mean by the age of the universe. And finally, I want to, I know I picked on some other topics, so I'm going to pick on myself now too. I want to question the claim we've made that we're going to get to 1%. 1% is really, really hard. How do we get to 1%, our route? We need 50 type 1a supernovae. Will that happen in the lifetime of HST? I really don't know. We need Gaia to be able to solve the 0-point source dependence. Will they do that? Well, we'll hear from Anthony Brown, but if they don't, we can't. So that will be hard. Can we really claim to measure Milky Way Cepheids, which are really bright, the same as those in distant hosts, which are really faint? And even if we're using the same telescope and instrument and check the linearity, can we really do that to 200ths of a magnitude? This is a little sweaty emoticon that I found. I didn't even know that existed. Or can we instead have 2 or 3 approaches, each getting to more like 1.5%, and average those together or cross-check them? I think we could get to about 1.3%. I don't think we could do much better than that because it's really hard, and I'm just being honest with you all. I'd love to say we're going gangbusters to 1%. It's a good target. It's the right way to go after keeping your systematics under control, but the route may just stack up that we can only get to about 1.3%. Then that's the way it is. So I'm going to end with this slide because this kind of amazed me when I saw this last week. This is actually from the Holy Cow team from Wong et al. I know we've been calling this the Hubble constant tension, but we have a bona fide particle, high-energy physicist in the room, David Gross. And, they always tell us, you got to wait till you get to 5 sigma. So are we allowed yet to call this a problem, or do we just have to keep calling it a tension? This is the guest part of my talk. Can we call it a problem?
Is arbitrary, but traditional in our field. Yeah, I think you should call it a problem.
All right. We have it from a high-energy Nobel laureate that it's a problem. Okay. Anyway, I will end there. Thank you.
Okay. So we have plenty of time for questions. Yeah, sure. And I think we have an extra mic as well.
So why do you need 1%? I mean, it's already 5.3 sigma.
It's catchy.
Already.
It's a good, 1%. No, what we really need, I'll tell you, strictly speaking, is you're maximizing the test with Planck if you can reach their error bars, right? Because until then, you're dominated by your error bar. Then once you're starting to add in quadrature, you're not getting that much. So Planck is well below 1%. So I could tell you a bunch of us, Wendy Berry, myself, Sherry Suyu, Tommaso Treo, who else was in that room many years ago. We came up with this 1% thing because it seemed sensible. I think it's the right target. I actually believe even if you don't get there, you want to have a target for systematics control so that, if statistics don't get you there, that's fine. So anyway, that's the answer. It's close to what Planck does, so it maximizes that comparison.
So the error bars is always depending, a satisfactory error bar also depends on how big is the quantity you want to measure. Given the fact that it's already 5.3 sigma,
that we're done?
I'm sure 1.3% is as good as 1%. The point is to have more than one measurement.
Sure.
Independent. That
Right. Well, that's why there are, and that's why I was highlighting the holy cow, just because I could say it has nothing to do with what we're doing. But the other thing I would say about that is if you actually want to diagnose what's going on, if we get to that point, then already different theories are saying, well, the Hubble constant should be, 70, 71. That's a set of theories. Others maybe, it should be 74, 75. So we need additional resolution, I think, within that separation to be able to say, models that predict too high or too low a change are favored or disfavored.
Hi. So I think another slightly interesting consideration to do regarding the voids is that the shoes and holy cow measurements are both local but not exactly the same volume. So we go out to about 0.3, 0.4, 0.5 in redshift. Typically that's the distances to the lenses. So obviously the local void issue doesn't matter. But I think also in terms of trying to find solutions to it, it means that we have a little leverage, few billion years of leverage to see if anything changed. So this may be the fact that there's consistency hints that there's nothing bizarre happening in this last bit of the life of the universe, which I think is something interesting for understanding this.
Right. But I still think the overriding statement about voids is you don't expect them from theory to be that big. You don't see them in the actual supernova Hubble diagram. So I'm not sure why we keep returning to voids, but that's me.
I'd like to beat that dead horse.
The voids? Go ahead. Here's my whip.
Just with a similar comment to yours about the BAO, right? So you can get all the way out to calibrating the BAO. You have the supernovae out there. You calibrate the supernovae with the Cepheids. You calibrate the Boss BAO measurements with those supernovae, and basically calibrate the sound horizon.
Right.
And it disagrees. There's no cosmology.
Right.
There's very limited cosmology assumption in there. Certainly a void doesn't impact that.
That's right.
And you're all the way out to z equals 0.5.
That's a very good point. So another way I think of saying that is if you use an empirical ladder based on supernovae, BAO, or whatever, that would soak up the void, and it doesn't in this case. You still see the tensions showing up like a scale problem at both ends and not something that gets rectified along the way.
Right. And let me, if I can add a further thing, I'd just like to echo Leach's point about why 1%. And rather than shrinking this uncertainty down, there's certain parts of this inference chain I just explored better. I'm really excited to all the talks that are about supernovae here, right? And if I'm trying to think of where are things going wrong, I'm not so concerned about tightening down errors on these different things, although that's helpful. But is there? I don't know. I have these qualms. Is there something about supernovae we're not understanding? Right.
Well, I will say from a measurement perspective that the two often go hand in hand. You sit down to go, look, here's this 3% error. It's been annoying. What if we do this to remove it or make it a 1% error? So we're going to cross-calibrate these two telescopes, and then boom, you discover, oh my gosh, that really was a 5% error, an 8% error. So I think, I guess I would say I think the process by which one tries to reduce errors to the smallest level often dredges up discoveries of much larger issues. You thought it was a small thing, you were doing something smart that would eliminate something small, and then you found that thing was big. When we moved to the LMC, we were observing those Cepheids to put them on the HST system. We were surprised there was a 400th of a magnitude change, whereas the lore was, this should be good to 200ths of a magnitude, 300ths of a magnitude. But it is what it is, and so you go along and you play whack-a-mole and you try to knock down all the small errors, and then you find one mole is like a grizzly bear.
I will second that one, but I just wanted to pin something for tomorrow. So you're commenting on something that I was supposed to have said at Cosmo Gold, but it isn't exactly what I said. So how we correct for reddening is taking into account, we use the stars at the tip. If you just naively do a color correction, then you're going to have the problem that you pointed out. And the technique that we've developed is analogous to what we developed for the Cepheids, but it's using the tip stars themselves. And I think we can do much better than what you said based on
Sure. What I guess, and this was my understanding of what it meant to use TRGB colors in other bands besides the I band, is that these are Padova models that I pulled. Each one of these colors is a span of 5 to 10 million years ages for stars, and those are actually pretty linear individually. And so that's good. But then when you go to other metallicities, it's linear.
I'll say more about this.
Okay, but I'm just saying it's linear at a different angle. And so
that's right.
The concern
and you
is
can make use of that because you know that they're the same stars. Anyway.
There's a really nice paper by Kristen McQuinn on this. I don't know if you saw this. It was just like a month ago. But where she points out the best thing you could do is to use a single slope because then you're not compounding the error, but you still have these residuals that depend on metallicity. So maybe we could talk offline about that.
Yeah, I think you can do a lot better than this. A lot.
So I had a question. In addition to the 1% precision H0 itself, obviously for any model, like what's going to be really interesting is understanding the z dependence and h as a function of z or h prime. And you haven't really talked about the accuracy with which you're going to do that. So could you comment on that?
To do this as a function of z?
Yeah.
Yeah. So,
or just
you know,
H prime.
this is where the problem separates out that supernovae relative to themselves and baryon acoustic oscillations relative to themselves, that is without a calibration coming from the earlier late universe, are much more powerful than the CMB or nearby for ferreting out how things change as a function of redshift. And so I said earlier on, and I assumed other people would talk about this, so far supernovae and BAO show from H of Z that it's very well described by W equals -1, you know, within 5% or so. And so so they're really, it's really in the wheelhouse of supernovae and BAO as middlemen, really, to work on H of Z. This is more like a scale problem. Start at one end of the universe or the other end. And so that's why, you know, people in the audience have said, what if something's happening before the sound horizon? How do you do this as a scale problem? There are ideas to do that. If you have predictions of other things to look for, you know, I think we would go after that for sure. If you have an idea how to solve this and it also predicts some H of Z behavior, we could look for that in the supernova and BAO data.
But do you ever just say how well you'll measure something like H prime? Is there
H prime?
Yeah, for example.
Q, we call Q naught. Q, J.
Yeah.
We do kinematic expansions of just kinematic terms, and yeah, there are a number of papers I can point you to. They mostly look like the Q naught you get from omega lambda minus 0.5.
Sorry, I'm just asking, what is the ultimate precision you will get from that?
Those are hard, but I think you're looking towards things like Euclid, W first, and DESI, and you know they're targeting getting to figures of merit of 1,000, which in human terms, that means an error of 1% in W and about 10% in W prime. And so we could transform that into H prime or Q naught. People don't usually do the mission specs in the kinematic quantities. They do it in these others. But we could help you transform that.
Okay, so we're getting distances to 1As and early hosts with SBF.
Distances to early hosts with SBF, yep.
Yes. And the technique is calibrated to Cepheids, so in theory it's isolating just the 1As in early hosts.
Okay.
If we do
and which Cepheid data is this from?
Well,
okay.
John will explain that.
Okay. Is this from ours or is this from the Key project earlier? Key project. Okay. Key project Cepheids to
If
Cepheid.
we did our work correctly as you would see it, what do you predict we would see about 1As and early hosts compared to in Cepheid?
Oh, well, you know, there's this small correction that people sometimes make, which we do, which is there's a tiny dependence on the mass of the host. And so once you do the host mass correction, I guess I'm thinking you're getting like 74? What are you getting?
We don't have that yet.
76. Okay. Yeah. So that's about what I would expect.
That was calibrating different?
So the difference there was they were using surface brightness fluctuations in lieu of supernovae. They can do that, right? They're doing it at supernova hosts, but they can also form their Hubble diagram just Cepheids calibrating SBF into the Hubble flow. And so he's saying you could remove supernovae. I mean, I've seen each step you can remove. And you seem to get about this, okay, it could be 71 and it could be 76 or something like that. I'm just saying, how come nobody is measuring below 67? How come nobody is getting below the Planck value? How do you ever converge as a mean of a bunch of measurements if none of them are ever on the other side of the thing? So, we could argue, and we should, about exactly how precise we are, but how do we get, who's measuring 65 and 63, So. Are you? All right. Well, stand up and tell. No, I mean, seriously, who in the late universe is measuring 63 or 65? Sandage and Taman are not here, but enough said.
You mentioned that you weren't sure whether you could get more supernovae with within the lifetime of HST. Is that also with the consideration that LSST is coming online in next year?
Right. If LSST comes online, will that help us? So I'm going under the assumption, which I'm pretty sure is true, but anybody can tell me if they think this is wrong. So we have been finding all of the supernovae in that small volume to 40, 50, 60 megaparsecs for about the last 20, 25 years. That people have been searching, and it's not a big volume. And so, except for the occasional supernova that's found just before it goes behind the sun, I don't think LSST helps you at all. LSST helps you to find further away supernovae, and they're going to find millions. But the problem is, in the volume that Cepheids or TRGB reaches, there's only like one a year, maybe not even. And so I think we find that one every year, except for Poisson fluctuations. So what would really help is getting the numerator down. If you could do better per supernova, better ways of standardizing type 1a supernovae, then you could win sort of linearly there.
So you mentioned that to get to 1.3%, you need Hubble to last another 5 years. What if it doesn't? And what are your plans with JWST? What are your hopes for JWST?
What are my well, obviously, if HST, I mean, the nice thing about if you are going for something and you fail, right, it isn't like a binary thing. So, if we get to, we have 38 observed now. So if we don't get to 50, we do root 50. I mean, this is the rate limiting step, so it's an important term. But, maybe we get to 1.5%, 1.6%. Then JWST comes along. I think people doing TRGB will have a fun time with JWST. I think that there's certain advantages for doing that. One of the things that makes it hard to do Cepheids with JWST is it's, two things. It's Cepheids have their big variations in the optical, so it's easy to follow them up, but it's hard to find them. And you want to make repeated observations to do Cepheids. JWST is a big, floppy, slow-moving telescope, and so the overhead hit is huge for revisiting things frequently. And so that's probably the biggest problem is, actually getting time to do something that's inefficient. And the giants will crowd you because the Hubble Deep Field people will go, hey, the Deep Field people will go, we could spend 80% of our time observing, and you're going to be like, I could spend 30% of my time observing. Yeah.
So I want to go back a little bit to the tension versus problem issue. So the 5 sigma, it's more of a philosophical statement, so don't worry about the slide.
Sure.
So the 5 sigma, and we have the particle physics here to actually confirm what I'm going to say. It's not there to be taken literally in the sense that it's 5 point something sigma, because we don't know the tail of the distribution so well. This is assuming everything Gaussian, and usually when you move into the tail, things are non-Gaussian, and so probably it's not 5. But it's more of a psychological issue of actually saying, if it was 3 sigma, then we can look into systematics, and maybe we can find something that will fix it, that will bring it down to 1.2 sigma, and it's totally acceptable. The moment it crosses that imaginary line, then the probability that it's a systematic that will actually close that gap becomes really small. And therefore, at that point, you should still be looking for systematic, of course,
Sure.
because you want to do a correct measurement.
Sure.
But then we will have
Right.
to start thinking what can fix it beyond
Right.
just.
Your
I made
point
a
is well
mistake.
taken. I meant this just sort of lightheartedly as people keep making fun of us as having tensions and do we need psychotherapists, and so I thought, maybe we just call this a problem. But in seriousness, I think there is a history in physics of having, the solar neutrino problem, the various ones. At some point, it's hard to say, if we just keep collecting data, it'll go away. Also, a point I'd like to make is particle physicists set 5 sigma because they don't know what energy that they're necessarily going to find something at. So they have to deal with a look elsewhere effect. We only have one universe. And so, if we have one parameter that we can check with the CMB, the only one that we can measure really well, then 5 sigma is actually too high, right? You actually should be having something probably lower when you start getting excited because, this can't be in a different universe. You seem puzzled, Lloyd.
Well, there are other parameters.
Yeah, but this is the only, if there's only one you can play the game with, if you can only measure.
I disagree.
What?
Yeah.
No, is there some, can we measure?
We're in the photon ratio from Big Bang nucleus.
Okay. But certainly not the range of energies that particle physics can look at, right? Where's your next particle going to show up in this collider? I don't know. I'm going to look for a bump. It could be anywhere. So that is a bigger look elsewhere.
So this is more like measuring, as you said, a single parameter. And 5 sigma is somewhat arbitrary, but there have been historical discoveries that come and go at lower than 5 sigma. So there's a long history, and that's sort of why this
Sure.
totally arbitrary. So
Sure.
statistically, of course, 5 sigma means it's there for sure.
Right.
If you just apply.
Right.
You don't worry about strange tails, and you just apply statistical theory.
Yeah.
So in particle physics, if we had the Higgs particle passed the threshold of being discovered at 5 sigma, of course by now it's 50 sigma. But if we found something like this, not for a strange bump, but for something, a null-like experiment, at 5 sigma, we wouldn't call it a tension or a problem, but rather a crisis.
Okay. Then we're in crisis, everybody. And I guess maybe a working definition of that is this is my 10th conference on this in the last 2 years. And so this is quite interesting. Maybe it's just an interesting threshold. This is interesting enough to get a bunch of people in, hot, sweaty rooms in Europe or wherever, all over the world, 10 times. So, we're in some kind of crisis. Identity crisis, whatever.
That's right. The fact that we're all here, it's not just tension. Okay, let's all thank Adam.